Am I correct with this assessment? Not correct. Okay, I'll assume everybody here was in the last lecture. Let's just recall that what we're KV, well-posedness, below VH minus 1 scale. So this is what we're trying to achieve. And again, let's recall exactly what we were interested in. Okay, so there was the KdV equation. Just recalling to everyone here that the equation that we want to study today is this one. Right? Moreover, what we want with the title is well-posedness and low regularity. In low regularity. But then we had this very extensive discussion about what this means, right? So I told you guys that below a certain threshold on the usual Sobolev scale, we cannot even make sense of well-posedness in the analytic sense, which was, let's write this. So if S is less than minus 3/4, there is no analytic well-posedness, or you don't have even smooth well-posedness, in the sense that if you take the map that from an initial data maps you to a solution, this is not even C3 below the scale, right? And the second bottleneck was the S less than minus 1. And you don't have continuity of, well, of the flow, right? So breaks down continuity if you're below S, below H minus 1, right? So last time I was motivating to you guys a transform that we need to use in order to make sense of what well-posedness should look like below the scale. Right, so then we wanted to define formally G to be a gauge transform that is given by, well, formally by its inverse acting on a function f. And then you may consider this as acting on a function f with high regularity. This is going to be something like f plus the inverse Fourier transform in the variable x of minus 1/3 times what I said to you guys, which was a bad interaction, right? In psi1 and psi2. So this was a gauge transform, and if we assume that the inverse of the map defined by this is well defined, and if we take a solution to KdV U and let the application of the gauge transform in U be given by Z, then what we said last time was that this new variable Z, after we change variables, this new variable Z satisfies the new equation, which is essentially of KdV type. And you have a bunch of nonlinear terms. These nonlinear terms are given by a sum like this, right? These are J linear, that is, they're terms, so these are multilinear operators. They're J linear operators applied in the variable Z all the way through, and they're non-local operators. So this is what we were discussing last time, that we get. So notice that here we had something that is linear on the left-hand side, and here's something that is quadratic, morally quadratic, if you scale on the right-hand side. And here it's the same thing, right? So since we're starting from J, from 2 onwards, we're starting with a roughly quadratic term, and then we have higher order terms, right? So the way that this should be interpreted is this gauge transform really is moving from the case where, well, here we were in a quadratic case. This is still quadratic. We might add a bunch of nonlinear terms, but then this kind of smooths out the solution U. And what our goal is, show that this new equation, which I think we called GKDV, this is small data, well posed in a Fourier-Lebesgue space. So in FLSB, where that space was the space of functions f, such that when I take the Japanese bracket to the power s times f hat, this is an LP, this is finite. And recall that here we needed to assume that s is greater than something, and what we're claiming is that this holds whenever s is greater than minus 2/3 minus 1 over 6p. Right, if we fix p, then we can guarantee some sort of well-posedness within those spaces as long as we take this threshold s, which is our regularity parameter, to be at least minus 2/3 minus 1 over 6p. And then we recall what this scale was. So this is minus 1/2 minus 1 over p, if I'm not mistaken. Then our threshold is better for p greater than or equal to 5. And this threshold here, I was telling you guys last time that this is the analog, so if p equals 2, here we get, by Fourier inversion, just the hs, so Boloff spaces again. This becomes minus 1. This becomes exactly the h minus 1 scale. And if we take a look at how the problem scales naturally, in analogy to how it scales in h minus 1, for LP, this becomes exactly the Fourier-Lebesgue space with this s, right? So what we're saying is we can guarantee well-posedness of this equation in these spaces, where if you just naively assume that the Kilip-Vigent result holds within the Fourier-Lebesgue scale, this would only go up until this point, and this is worse than our bound. So this is roughly the bottom line that we want. If you want a picture, would be something like this. So if here you have, maybe here you take p equals to 2, p equals infinity, you should have the Kilip-Vigent result going all the way to minus 1 here. And then when we have infinity, this should go to the minus 1/2. So this is the theoretical line that their result gives. And then what we are saying here is that we have this minus 2/3 minus 1 over 6p. So that for our result, we get something like this, right? So we get a little bit better here. So this is minus 2/3. But then when we take p equals to 2, this is minus 2/3 minus 1/12. So this is minus 3/4 again, right? So then this jumps a little bit backwards. So our line will be something like this, right? So then there is a threshold here where one starts becoming better than the other, and this threshold is p equals to 5, right? So this is the picture of where our result gains over there. So just below, from this scale onwards, and we gain something over their scale, and here we don't. But the second kind of remark to be done here is that we don't even, there is no result in this scale, even if you try to use the clip-vision techniques. So since the kind of spiritual objective of these lectures is to give you a bunch of nice open problems, this is a nice one. So try to prove some well-posedness result for KDV on the real line above the scale for p different than 2, right? For p above 2. For p equals to 2, there's, well, this is an Annals of Math paper, so you guys might find it a bit tough. So this is the clip-vision paper. It is very nice, but it is already quite tough. For p different than 2, I think new techniques are required. I think for the periodic case, if you're working instead of the real line on the torus, then it's a different game. I think I was talking to Simon these days, and he recalled that there's this paper by, I think, Molnar and Capella, where they actually do it in this scale for the periodic KDV. But yeah, that is for the periodic case, where you don't have as many bad interactions, right? So maybe a first step would be trying to understand that case as well. Right, and this is just to put in context what we're doing. Okay, very well. So this is our goal. We're going to try to recall a bit what the strategy was, and then see what we can do from there. Right, so let's recall that solving this equation here is the same as solving an integral equation, right? So the usual kind of trick that we do, use the Duhamel formula. The Duhamel formula. Well, we may write u at t as e to the minus t dx cubed of u naught, the initial data, plus integral from 0 to t e to the minus t minus s dx cubed. And here we get dx of u squared ds, right? I did nothing, just wrote the integral equation, which is equivalent to this thing right here, right? So we applied this guy, so minus this guy to both sides, right? So if we apply that guy to both sides, e to the t dx cubed, so this guy dies, and this guy also dies. So what we get is e to the t dx cubed u of t equals u naught plus integral from 0 to t e to the s dx cubed of dx u squared ds. This is a u squared. This all depends on s, right? Okay. So right now, what do we do? Well, let's say that we call this guy a new function, a function v of t. And we try to find an equation for that guy. So the idea is, well, let's try to differentiate it in time. If we differentiate it in time, then we get rid of this guy, and we just get e to the t dx cubed of this guy applied on dx u squared at t. And we could try to pass the Fourier transform on both sides. And if we pass the Fourier transform on both sides, the Fourier transform are only in the variable x, right? This commutes with the time derivative. Well, we should get something like this. And if we expand the computations that go into this guy, we will get that the right-hand side is simply I times the integral of e to the minus it psi cubed minus psi 1 cubed minus psi 2 cubed, all that times psi times v hat of psi 1, t, of course, v hat of psi 2, d psi. And this is the integral in the variables psi 1 and psi 2, but since we had this bilinear term here, they had to be coupled somehow. And they're coupled by being in a convolution plane. Right, so this means nothing but the fact that I can choose freely whichever variable I want to integrate on. It could be psi 1, psi 2, or even psi, but I just have to switch variables, change variables here, right? So this is just an integration over this convolution plane. Okay, so I got a nice expression for v hat. It's a nice integral equation. And let's start maybe simplifying things a bit, right? So maybe we say, instead of writing this whole monster here in the exponent, we say that that is a function phi of psi 1, psi 2, which is, well, so let's say that minus this guy is phi, so this is minus psi cubed plus psi 1 cubed plus psi 2 cubed, which has a very nice formula. This is just minus 3 psi times psi 1 times psi 2 in this convolution plane, if psi is the sum of psi 1 and psi 2. Okay, so this is cool. This is a very nice, cute formula. And what do we want? Right, so we have an integral that, as I said, we can choose the variable in which we're integrating. So we can think that we're integrating this guy over psi 1. Okay? So this is a function of psi 1 and psi 2. But you see, if psi is fixed, then psi 2 is defined immediately as long as I define psi 1, right? So then this is a function of psi 1 alone for every psi fixed. And as such, well, we want to, you know, whenever we're working with a PDE problem in dispersive equations or in harmonic analysis, we want to take a look at, hey, if I have an integral, and this integral has a phase function, I want to know where this phase function degenerates, right? Because if it doesn't degenerate, then I can induce some sort of additional decay from my phase function. I can just integrate by parts, and I can keep on integrating by parts and get more and more decay, use the stationary phase method, right? So basically what we want, the next question is, where are the stationary points of this phase, right? And these are stationary with respect to which variable? Well, there is one variable of integration, which is psi 1. So we have to analyze where d psi 1 of phi equals to 0, right? And if we do that, so this happens if and only if either psi 1 equals to psi 2 or psi 1 equals minus psi 2, right? So the bad interaction, so what I'm saying is, at the end of the day, if we somehow know that we're integrating over a region in this phase space where psi 1 is very far away from being equal to psi 2, and xi1 is also very far away from being equal to minus xi2, then we're good. We should be able to integrate by parts, get a lot of decay, our problem is great, and life is good. But this is not the case, right? So for a general function here, it could have that we're messing with the bad interactions all around. So what we need a way to kind of deal with these bad interactions, and that is exactly the idea behind this extra indicator here. So what we do is, well, let's look at this integral equation, and let's split it into two parts. Let's split it into one part where we're kind of avoiding these bad interactions, and that is wonderful. And let's keep another part where we're exactly at the bad interactions. So you write then the derivative of that guy as I times the integral of e to minus it phase function times psi v hat of psi1 v hat of psi2 d psi. And here we write a union complement of A, and the set A, it's going to be basically the set where these interactions are going to be avoided, right? So let's not worry too much about the set A. I think maybe at the beginning of next time I'm going to tell you guys exactly what it is and how it enters our computations. But the way that you guys should think is the set A is exactly the set where we're avoiding these bad interactions, right? So we keep two parts, right? So we have this guy, and we do a fine trick, which is let's write this whole thing as a derivative of a time integral. And this is going to be the derivative of the integral from 0 to s of, well, I split this integral into two parts, so I just write the first one as this guy here, where I said that everything is good plus a part which I kind of integrate by parts, which is the integral e to the minus t phi over minus 3 psi1 psi2 v hat of psi1 v hat of psi2 d psi. So I take a time derivative of this minus integral on the complement of e to the minus I t phi minus 3 psi1 psi2 time derivative of whatever is here. And I know this is a bit much, but let me explain what's going on. So this is all a whole integral in time. So this is dt. And what is going on here, right? So this is a derivative in time. And what depends on time here inside? So these guys are time-dependent functions, and this is a time-dependent function only on the exponent, right? So if we're differentiating this guy by chain rule, I either get the derivative falling into two of these guys, which is exactly the term that I'm accounting for here, or the derivative falls into this guy. When the derivative falls into this guy, I get minus I times phi. But phi is exactly, well, minus 3 times psi, psi1, psi2. So then I kill off this guy here, and I get exactly the multiplier that I had before. So this is just a very fancy way to write exactly the integral over the complement of A of this guy. I'm doing nothing. I'm just writing something in a fancy way, right? Okay, so then by writing it in that fancy way, what do I get? Well, I get that guy was, well, there was some initial term, which was this guy. Since I took Fourier transforms, I had to account for that guy. plus, well, the first term that I said, it's this one, where we're kind of keeping only the good interactions. So I just leave it aside. Since the interactions are good, I just leave it as one nice term. So this is the integral from 0 to t, integral on a, e to the minus I t prime phi, psi times v hat of psi 1, v hat of psi 2, d psi dt prime, right? So as promised, there is one nice term in the beginning, and we keep it. And the next one, well, this is an integral in time, and then this is a derivative in time, and then we're integrating in time. So I just get two terms, right? So you get two boundary terms of the form integral on the complement of a of e to the minus I t prime phi over minus 3 psi 1 psi 2 v hat of psi 1 v hat of psi 2 d psi, and this is evaluated at either t prime equals 0 or t prime equals t. So it's not an integral without a term without a time integral. And then I get a third term, which is of the form 1/3 I times integral from 0 to t. And then I use the fact that I have here a derivative in time. But then, well, I have an equation for dt of v hat, which is this one. So I can throw it back into itself. I use the chain rule here. I use that equation, and I get something like the integral here on time, the integral over the complement of a. And on the convolution plane, that right now is not the previous one, it's one defined by a subsequent change of variables, which is like psi 1 equals psi 1, 1 plus psi 1, 2. I have some extra variables here to spare. And I get e to the minus I t prime phi. But then since I substituted this again inside, I have to put one more phase factor term into this. And this is going to be another phase phi 1. I'm going to write it in a bit what it is. This is all divided by a term of the form psi 2, v hat of psi 1, 1, v hat of psi 1, 2, v hat of psi 2, and then we integrate over whatever psi variables we have and over the time variable, right? So what we did here was just, expand, use the product rule here, use the fact that we already have an equation for this guy, and just swap out new variables. And here, this phi 1 is just phi of psi 1, 1, psi 1, 2, right? Which was exactly minus 3 psi 1, psi 1, 1, psi 1, 2, right? Whenever this condition is satisfied. So what we have is, well, here we had a good term. We set it aside. Good terms are never going to be changed anymore. We set it aside. We estimate them later on. Here we have a boundary term. This is trash. We have to get rid of the trash. We're going to get rid of that later. And here we get a term where we have an integral which is still susceptible to good and bad interactions, right? So the natural thing is, well, here in the previous step, what did we do? We swapped where the interactions were good and bad, and we split it and integrated by parts further. So basically what we're going to do is just iterate this, right? So this is the game plan for us. So let's just write down what we're going to do. So let me just write this as, so this one, so this is a good term in the sense that this is ready for us to apply a nice multilinear estimate. If we work a little bit, we get an estimate for that term. So this is a boundary term which is trash, And this is an iteration setup, right? So we iterated once. And the same idea is, well, let's divide these new variables here. And of course, there's one more term that I didn't tell you guys. This is just accounting for when the derivative falls on this guy. When it falls on the other guy, we have analogous terms for psi2, right? So we get psi2 1, psi2 2, and so on and so forth, right? OK, so we get an iteration setup. And so what we need to do is, so for good term, we'll want to keep it as it is. Later on, some multilinear estimate's going to jump in next time and save the day. The boundary terms, well, we want to get rid of that. We want to get rid of it by the gauge transform. So this is where the magic of the gauge transform appears. It's going to kill all the boundary terms. It's insane. It's the perfect kind of transform that is going to just like kill the boundary terms whenever we're working with them. So you see, there's this first boundary term, but then when we use this iteration that we did in the previous step right here, more boundary terms will appear. But then when we start jumping in and using this change of variables back, in these equations, they're going to be like it's a domino effect. They all kill each other, and they all vanish at once. So this is the magic of the gauge transform. So the gauge transform is going to kill all the boundary terms, and is going to help us massively. And then for this, we're going to repeat. So let me just show you guys how we do it in one more step. And then I'm going to introduce some more, let's say, abstract notation that we're going to use. OK. So can I erase here, guys? Is it fine if so everybody is already back, already recalling what the basic setup is, right? So if there is any doubt, you just ask me. So let's look at the iteration setup, right? So we have an integral. So there is a time integral, but since we did it we make the time integral disappear and reappear again. Let's just work with the integral inside. So I have integral on the complement of a, and also we're in this new convolution plane again of e to the minus I t prime phi plus phi 1 over psi 2 v hat of psi 1 1 v hat of psi 1 2 v hat of psi 2 d psi. So then we separate it, we split it into two terms, right? As we did before. So this is an integral over the complement of a intersection a1, which is the same set as a, but with all the variables replaced by their analogs for psi 1, psi 1 1, psi 1 2, and psi 1, right? Of this whole thing, plus the same thing on the complement of this whole thing. And then, what do we want to do? Well, we want to say that this first term, since we're kind of where this phase here is very small, but then the second phase is not small, this is kind of dominated by the second phase. And the second phase, since it doesn't vanish, since it's not stationary, well, we can use the stationary phase method and still get a lot of decay by just the fact that we're in the good set for this phase. So this is a good term, all right? So this is a good term. So we get decay from the phi 1 part. And this, well, this is the term that we want to expand. So we write it in a very neat way. So what we need to do in order to expand that is a clever way to write it in terms of some multipliers. Okay, so let's say we zoom into this guy. So this guy equals. So this is the integral over the complement of A intersection the complement of A1. And here we get e to the minus I t prime phi plus phi 1. And we can write it as something like 1 over xi times xi1, 1 over xi1, xi2, and all of that times xi1. Oops, sorry. So this should be xi1, xi1, 2. And this should be xi1, xi2. I think that is correct. This should be xi1, 1. Yes. And this should be xi1, xi2. Is that correct? No. Yeah. This should be xi1, xi1, 1, xi1, 2. Since we kill off all the terms instead, except for xi2, times, well, v hat of xi1, 1, v hat of xi1, 2, v hat of xi2, d xi, right? So I did nothing. I just, this 1 over xi2, I just wrote it in this funny way. But the nice thing is, this is now exactly the phase phi 1. Multiplied by a constant, right? So this I write, well, I can write it as minus 1/3 integral AC A1C e to the minus I t prime phi plus phi 1. This, I'm going to call this K naught, and this I'm going to call K1, right? So I get a multiplier K naught, I get K1. And here I get phi 1 times v hat xi1, 1, and so on. OK, so you might be wondering, what the hell is this guy doing? So he's just like doing some algebraic tricks here and there. Yeah, that's actually true, but it's going to allow us to integrate by parts. Why? Well, so this guy, phi 1, is doing nothing wrong. So why don't we write this as phi plus phi 1 minus phi, right? So this guy, so this whole sum, this is 1/3 of the integral on the intersection of the bad sets of e to the minus I t prime phi plus phi 1 times phi times the multipliers times our v hat product, right? So there's a first sum, that is this coming from the phi term. And this I want to say, this is the term that is well controlled. Why? Well, because here phi I assume to be in the bad term, therefore phi is assumed to be very, very small. So this should not be contributing to a lot in this sum. So this is going to be absorbed into a nice multilinear term that we can estimate. So this is going to end up being a good term. But then here we get minus 1/3. The same thing. But here we have phi plus phi 1, which is exactly the derivative of the phase modulo an imaginary constant. So here, I think what we get is something like minus I over 3 times the derivative on the t prime variable of e to the minus t prime phi plus phi 1 times the multipliers times the v hat And then you see, now we have this integration. So if we go back to the term that we had a term of this form, which was an integral of whatever we're integrating up there. We split this inner integral into a bunch of terms, into 3 actually, 2 of which we said were fine. We got good terms. We can estimate them later on. And the last one is a time integral of this whole term here, which has a time derivative in itself. So if we write it, well, we do the exact same integration by parts argument again. So this is the derivative of this guy. I can write it as a derivative of the whole integral minus the derivative, well, keep the phase, differentiate this guy. So then if we do that, well, then we get simply, well, a phase function times this guy, but with no time integral. We get a boundary term. And then the other term that we get, the derivative falls into either this guy or this guy or this guy. But then we know how to compute the derivative of this guy. We can plug in the equation and repeat the process. So that's what we do. So yeah, so this is basically the method that we do. And I'm going to write it in more succinct terms. Let's be more precise. So as you see, we're getting more and more variables at each time, right? So here in the first iteration we got xi1 and xi2. And then in the second iteration we got xi11, xi12, and xi2. In the third iteration I'm going to get 2 more variables depending on where this guy hits. So this induces us a natural tree-like structure. So we're going to associate variables to a tree. And this is going to be to a binary tree, right? So if we have, well, let's say if you have this tree, right? So then how do I associate the variables in a multilinear operator to this guy? We go from the root node. This is empty set. This is just xi, right? So this is just xi. And these two guys, these two nodes, this is the set 1, and this is the vertex 1 and vertex 2, which are, of course, associated with xi1 and xi2. And we go in the exact same way down the tree, right? So we have xi21, xi22, xi121, xi122, xi111, xi112, right? And this tree just says that, well, whenever I have a vertex here, then the variables underneath, their sum is the one above, right? And we're going to get these bunch of structures whenever we're applying this integration by parts argument. So, OK, so we're going to use these structures, and we're going to denote a tree by this curly T, right? So all the structures that are going to appear in our proof are going to be binary trees, so we're going to denote them by that. The second thing that we need to define as well, here note that we got phi plus phi 1. So whenever we're doing this integration by parts step, we get an additional phase factor. So we're going to get, so whenever, what I'm saying is that at each step, whenever we're integrating over the variables on a tree, T, then the phase that we get is going to be something like this. It's going to be minus xi cubed plus the sum of xi star cubed, where star is a leaf of T. And what are leaves? Well, leaves are exactly the terminal nodes, right? So this, and this, these are all, these are leaves, right? So this is the total phase of our tree. And in analogy, well, for star, for a vertex star in a tree, then we define the multiplier k associated to that vertex as minus 1 over 3 psi star 1, psi star 2, whenever that vertex has two children, right? So that's exactly what's appearing here. So here we had the vertex psi, we get two children, we get this kind of multiplier. We get psi 1, it has two children which are being integrated again. We get this other multiplier, right? So we get a multiplier of that 4. And finally, let's write v star as simply v of the variable psi star, right, for shortness. So how do we rewrite whatever we did in this new language of trees? So let's try to do that. So I think I accidentally did the perfect calculation to just erase very few parts of what I did and just and switch back to the notation. So let's go here. So here, well, we have psi equals psi 1 and psi 2. So we're exactly on a tree. It's a cherry. It's a cherry tree. So we're, instead of writing this, we're going to write, well, for shortness, that we're integrating over this tree-like structure. The phase is exactly the phase associated with this tree. So we write it as the integral over psi of t. And here we get, well, psi is exactly the phase psi of t, where t is this cherry, multiplied by the empty multiplier times these two guys. So I'm just writing it in our new notation, right? So we can write it as such. And let's just use the notation for this in terms of, and let's be even more succinct, and let's call this an operator I. It's a multilinear operator. This is associated with the tree. This has a certain multiplier associated with it, which is this guy. And it's applied on certain functions, right? So let's say this is v1, v2. Okay, so that is the notation that we're going to use. And what is exactly the next step? So the next step, so this one here, right? If you want to write this in a new way, what do? Well, we simply write this guy. We break up, what we're doing here is breaking up the multiplier into two parts, multiplying this by I restricted to R3, indicator of A, K naught psi, V1, V2. And this is what I said was the good guy, plus I restricted to R3, indicator of the complement of A, K naught psi, V1, V2, right? So this is exactly the decomposition that we're doing there. So this was a good term. And this is the term that we wanted to expand. So we expand that. And how do we, let me see if I want to keep it here. Well, let me erase these things. So then I say, well, those terms are, well, the good guy. I'm going to say that it's the Fourier transform of a certain non-local operator n associated to my tree and associated to my function v. And this is definitely related to that expansion of the variable z that we did before. I use the integration by parts argument on this guy. And since I use the integration by parts argument on that guy, I get the derivative of an I term with the tree that I had. This multiplier and v1, v2, because now I was integrating by parts, and then this guy just vanishes when I integrate it by parts, and I get an extra term which is associated with a new tree. And what is this new tree? I have to either append 2 extra vertices to this guy or to that guy. So either I get this tree, my multiplier then becomes k1 psi 1 v1 v2, and then the analog for the vertex 2, right? So I'm just writing exactly what we're doing here in terms of this tree notation. And then if I reiterate, this iteration scheme actually carries over in a nice way. So this I can write it as, well, there's a first term which is the Fourier transform of this nonlinear non-local guy. And as I said, this was a good term, so I keep it. This guy, I'm going to say it's a Fourier transform of some other term, which I'm going to use the letter b for boundary. So this is what we need to get rid of. And then these are the guys we're iterating stuff. So this, well, just following exactly the same kind of argument that we used here, where we sum and subtract stuff, what we get as well, get a term like I of this tree right here. The multiplier is something like this, psi 1 plus a c integrals a1 c psi of this guy times k naught k1 v1 v2 plus an analog. So this was the term where I collect everything that I could discard, and then I got a term of the form, well, I get this same tree minus the integral a complement a1 complement k naught k1, and here I get the multiplier associated with my tree v1 v2, which is exactly this integral term corresponds to this guy here, and some analog, right? So analog. So then right now it's hopefully clear what we're doing, right? So we're just translating whatever we did here into this new language that we adopted, right? So we're adopting a more succinct notation. And so here we define this n term by just like, it was the first term which was good. Then the next n term, how is it defined? Well, we have this new term here that I said was the terms that were good already before. So I'm defining this as the Fourier transform of the n term of this new tree, right? So this is good as well. And the same for 2, which gets a flipped tree. So then I get this term here, which is the term that I want to use to integrate by parts. And I go on, right? So this is hopefully a clear process. I have to define the multipliers that I'm putting in to my good terms. They're going to be a complicated combinatorial structure, but what you should take with you guys today is that these are terms which are fine. So we can control them in standard ways. We get boundary terms, several of them. We get these terms which we can control, and you get the iteration terms. So just so that we can go on, so next time I'm going to explain to you guys briefly how the gauge transform enters the whole thing. Formally, we have that the derivative of my modified, my kind of flow translated solution is, well, it's going to be a sum from j from 1 to n minus 1 of a sum over all trees of size j, boundary terms associated with those trees. Right? So I'm saying that, well, there's boundary terms, a bunch of boundary terms. They might be coming on from several trees. Well, we just collect them here. I'm going to have another sum. And this one is going to be, again, over all trees. But right now, I'm going to collect the terms that are good for all trees. And note here that I had this kind of term here, and I get the flipped trees that I had. So they are isomorphic. I can combine them into one tree. So I get over all trees and some guy like this. And then I get the final terms, which are these contributions, these iteration contributions, right? So I get something like t over the final step of trees. And these are the last terms that I'm going to be calling them this m terms of trees applied to V. And just again, just driving the point home, so these terms are boundary terms. We need to get rid of them. So they're bad. In whichever function space we're trying to deal, they're not going to be easy to estimate. So they don't have a time integral to save us at the end of the day, right? So they're going to be bad. We need to get rid of them somehow. These terms, they're nice. So the multiplier is nice. It decays very well. So we can just basically deal with these terms in standard ways. So these are not of our concern. And these guys, well, the multiplier that we have here is a multiple of the phase. So since it is a multiple of the phase, we can use integration by parts and reiterate. So when we do this, we can take the limit when n goes to infinity and just write something like this. So in the informal terms, these guys should all vanish at infinity if things are small enough. So these guys, we keep on iterating, we keep on adding terms here, we keep on getting deeper and deeper terms. And what we should have morally is something like this. We should have an equation for V of that kind. And what we're going to be discussing next time is how from an equation like that we can use the gauge transform to kill all the boundary terms. In addition to that, after we kill all the boundary terms with the gauge transform also does the nice favor to us that it kills all the trees that are not of either this form or this form or this form. So whenever we use the gauge transform, if we say that we apply the gauge transform to V, we not only kill all the boundary terms, but the only trees appearing here, or we're going to change the multipliers a bit, but that doesn't matter, are going to be of either this single tree, or of this form, or of this other form. And then we just simplified our lives so much. So we have a very, so the combinatorial structure, we could have weird trees coming up right here, right? So we could have a very rich combinatorial structure. What we're saying is that the gauge transform kills all of them. But yeah, maybe that's better left for next Thursday, right? So that's what we said. Yeah, okay. So thank you, guys. Questions? If not, maybe we can resume next Thursday.